Hi everyone. In this talk, I'm going to introduce our recent work on the training dynamics of multi-head softmax attention model for in-context learning. This is a joint work with Hijun Xin, Tianhao Wang, and Joanne Yang at Yale Statistics. Here is the agenda. First, I discuss the basic concept including ICL and multi-head softmax attention. As a warm-up, I'll demonstrate using single-head attention for ICL. Then I'll present the main results on the three phases training dynamics, followed by some interpretations. Let's first look at the basics of ICL. In this work, we follow the ICL framework proposed by Garg et al. The prompt consists of a sequence of XY pairs, where each Y is functionally related to X in an unknown but consistent manner. A query is appended at the end of the prompt, and the answer YQ is from the same function of XQ. The goal of ICL is to find a model that takes both the prompt and query as input and predict the desired YQ. Transformers are particularly well suited for these ICL tasks as they effectively extract features from the sequential input. And the incredible capacity of transformers comes from the use of the softmax self-attention mechanism. This mechanism maps a sequential input to the sequential output. For each position in the sequence, the input is transformed into values, keys, and queries through linear transformations. The model then computes a softmax probability over the entire sequence using the inner products of the keys and queries. And finally, it aggregates values based on these softmax probabilities. Today's large language models typically employ the multi-head version of this mechanism. This approach involves running each parallel attention head simultaneously. Each head processes the input independently, and their outputs are combined using the output projection matrix. The final piece of the puzzle is how to train a model like GPT for ICL tasks. The training process typically involves two phases, pre-training and fine-tuning. In both phases, the model uses the cross-entropy loss. The difference between these two phases is shown in the table. Pre-training typically uses a larger dataset than fine-tuning. In terms of the training methods, pre-training usually involves unsupervised next token prediction, while fine-tuning may involve supervised tasks aimed at directly improving the model's answer quality. In this study, we are using a training paradigm closer to the fine-tuning phase, and our goal is to investigate how training enables the multi-head softmax attention model for ICL. Let's look at some previous training work on this topic. Zhang et al. Explored training a single-layer, single-head linear attention on linear data. Here, the linear attention replaces the softmax with simple matrix multiplication. They also consolidated the QK matrices into a single weight. With these simplifications, they find that the attention mechanism eventually learns precondition gradient descent. In a similar vein, Huang et al. Examined a comparable setup. However, their analysis was confined to covariates coming from an orthonormal basis, and they operated under the assumption of noiseless data, which somewhat limits the realism of their findings. Let's come into the setup of our study. We consider in-context learning with multitask linear regression, which encompasses standard linear regression as a special case. In the left picture, this prompt and query constitute one sample in the whole dataset. Each X is independently sampled from a d-dimensional standard Gaussian, while Y is of dimension I. The same is for the query. When we look closer at such an XY pair in the sequence, each coordinate of Y linearly depends on a subset of X. Consequently, this setup is termed multitask linear regression. Let DI be the size of task I support. We assume there is no overlap between any two subsets, and thus D is equal to the summation of all the DIs. The subset structure is unknown to us and left for the model to learn. It's also worth noting that random coefficient GI for task I is shared across the entire sequence, but the noise is independent for each XY pair. We model the random coefficient Gi with zero mean and covariance determined by the constant lambda times the identity matrix. We assume that the noise is sampled from independent Gaussian with variance sigma squared. We further let Z be the matrix form of the prompt, which combines X, Y together, and let ZQ to be the concatenation of XQ and 0. With the multitask linear regression data described before, we train a multi-head softmax attention model with each parallel head. Here, we input Z for the keys and values, and input ZQ for the query. This is equivalent to the standard multi-head attention with causal mask, but only taking the last position of the output sequence. We use the population mean square error as the training loss, and consider gradient flow on the model parameters, which are the value, key, query, and output projection matrices. We aim to answer the following questions. First, does gradient flow converge? If so, what's the learned model? Second, does multi-head structure offer any benefits compared with single head? We will provide affirmative answers in the region where there is a constant ratio between the dimension and the sequence length. We also assume that each task is taking a constant portion of the total dimension. And we consider the number of heads to be larger than the number of tasks. Previous works does not apply here because, firstly, the analysis for softmax adds to the difficulty in terms of the nonlinear effect. Secondly, we are considering multi-head attention, and there will be cross-head interference that's not handled by previous work. Lastly, we are not restricting ourselves to non-orthonormal data. Before we introduce the main results, let's consider the case of single head and single linear task for ICL. We can make a guess of what could be a good ICL model. In the following, let's combine the OV matrices into U and also combine the QK matrices into W. We split U and W according to X dimension and Y dimension. We set UX and WY to be 0, and leaves UY and WX to be the effective weights. Then we have this reduced model. Let's take a single task. And by the isotropy of X and also the covariance of G, it's reasonable to set WX as a simple identity matrix. Meanwhile, UY will remain a scalar. Under this guessing, the model is implementing an exponential kernel regressor, where it aggregates Y in the prompt according to the similarity between query and keys in the X part. In fact, it can be proved that this guess model is actually optimal for single-head softmax attention. Let's think of the case for multitask and multi-head. If you have the number of heads larger than the number of tasks, it could be that each task is handled by a unique head. Let's make this point clear. If a head is associated with a task, we can set UY and WX to be low-rank matrices, and they are only supported on a task subspace. This will not cause any cross-head interference, and the final output of the model will be a simple summation over all the tasks' output. In this work, we focus on the case H is larger than I, and ask ourselves whether the dynamics can indeed learn such a task-head correspondence. In the following, let me introduce the main results on the training dynamics. We identify 3 training phases and find a limiting model to have the pre-mentioned task-head correspondence. Before we dive into more details, there is a crucial property of the dynamics, which states that with proper initialization conditions on the weights eigenvectors, we can leave the dynamics to the spectral domain. This means we only need to check the singular values of these matrices. Specifically, the unwanted UX and WY matrices, which we are set to 0 at initialization, will always remain 0. Using this lemma, we have a simplified form of the model. Let's denote the singular values of the product of O and V as mu, and the singular values of the product of K and Q as omega. We can draw a similarity to the diagonal linear network with quadratic reparameterization. It's known that this quadratic reparameterization has an implicit bias that adapts to the sparsity or low-rank structure in the data while initialized with small weights. Let's discuss the initialization that gives us such a good property. We simplify by ensuring that the OV and KQ matrices share the same singular values at initialization. We initialize all the eigenvalues to be small to leverage the implicit bias of the square root parameterization. For the QK matrix, we initialize all the eigenvalues to be equal, which gives an identity matrix. For the OV weights, we use randomized initialization. This is crucial as it breaks the symmetry among heads. To illustrate, consider the eigenvalues mu across each head, collected into a matrix M. In this matrix, each row represents a task, and each column represents an attention head. We define the optimal head for a task as the unique maximizer in the row of M corresponding to that task. In other words, the model's output for a particular task is primarily influenced by the optimal head for that task. We further assume that any two tasks cannot share the same optimal head. Under this initialization, we identify three phases in the gradient flow dynamics. The first is the warm-up phase, where the optimal head gradually becomes more focused on its corresponding task. To give an overview, we can approximate the couple dynamics of mu and omega with these two PDEs. Here, we only consider the time derivative of the logarithm ratio, as this will help kill some cross-head interference terms. We denote by omega bar the average of omega on each task's support. The initial advantage of the optimal head in mu will translate into an advantage in omega through the second equation, which will in turn boost the advantage in mu through the first one. Therefore, the optimal head will gradually dominate. The second phase is the emergence phase. During this phase, we focus only on optimal heads that dominate. We solve the couple PDE for this optimal head, as the cross-head interference will vanish at this point. This phase is characterized by a rapid growth of omega for each optimal head. The final phase is the convergence phase. The same as before, we only focus on the optimal heads. Here, the weights of the optimal heads gradually converge to become the optimal single-head attention for their corresponding tasks, while the weight of the non-optimal heads will remain small. As a wrap-up, we provide more interpretations of the convergence results. First, the head-task association is determined by randomized initialization. In the limiting model, each task is managed by a unique optimal head, identified by having the largest eigenvalue mu at initialization. Secondly, the optimal head converges to perform the best exponential kernel regression with corresponding task. Lastly, the implicit bias of the quadratic reparameterization ensures a low-rank structure, allowing each head to focus exclusively on one task while ignoring the others, as is shown in the above equation. Let's compare the performance of multi-head attention to single-head attention. We consider I-homogeneous tasks. The first lemma provides an upper bound on the MSE error at the convergence point for the multi-head attention model. The second lemma shows a lower bound for the single-head attention model. Clearly, the multi-head attention can be I times more efficient than the single-head attention, where I is the number of tasks. The efficiency of the single-head attention model stems from its limitation in attention pattern, whereas multi-head attention allows each head to have different attention patterns. That's all for the talk. Thanks for your attention.